Enforcing constraints. Let's think about correctness in the context of the ideas around unbundling databases. Unbundling databases on page 499. We saw that end-to-end duplicate suppression can be achieved with a request ID that is passed all the way from the client to the database that records the write. What about other kinds of constraints? In particular, let's focus on uniqueness constraints such as the one we relied on in example 12-2. In Constraints and Uniqueness Guarantees on page 330 we saw several other examples of application features that need to enforce uniqueness. A username or email address must uniquely identify a user. A file storage service cannot have more than one file with the same name. And two people cannot book the same seat on a flight or in a theater. Other kinds of constraints are very similar. For example, ensuring that an account balance never goes negative, that you don't sell more items than you have in stock in the warehouse, or that a meeting room does not have overlapping bookings. Techniques that enforce uniqueness can often be used for these kinds of constraints as well. In Chapter 9 we saw that in a distributed setting, enforcing a uniqueness constraint requires consensus. If there are several concurrent requests with the same value, the system somehow needs to decide which one of the conflicting operations is accepted and reject the others as violations of the constraint. The most common way of achieving this consensus is to make a single node the leader and put it in charge of making all the decisions. That works fine as long as you don't mind funneling all requests through a single node even if the client is on the other side of the world, and as long as that node doesn't fail. If you need to tolerate the leader failing, you're back at the consensus problem again. See Single Leader Replication and Consensus on page 367. Uniqueness checking can be scaled out by partitioning based on the value that needs to be unique. For example, if you need to ensure uniqueness by request ID, as in example 12-2, you can ensure all requests with the same request ID are routed to the same partition. See Chapter 6. If you need usernames to be unique, you can partition by hash of username. However, asynchronous multi-master replication is ruled out, because it could happen that different masters concurrently accept conflicting writes, and thus the values are no longer unique. See Implementing Linearizable Systems on page 332. If you want to be able to immediately reject any writes that would violate the constraint, synchronous coordination is unavoidable. The log ensures that all consumers see messages in the same order, a guarantee that is formally known as total order broadcast and is equivalent to consensus. See Total Order Broadcast on page 348. In the unbundled database approach with log-based messaging, we can use a very similar approach to enforce uniqueness constraints. A stream processor consumes all the messages in a log partition sequentially on a single thread. See logs compared to traditional messaging on page 448. Thus, if the log is partitioned based on the value that needs to be unique, a stream processor can unambiguously and deterministically decide which one of several conflicting operations came first. For example, in the case of several users trying to claim the same username, every request for a username is encoded as a message and appended to a partition determined by the hash of the username. A stream processor sequentially reads the requests in the log, using a local database to keep track of which usernames are taken. For every request for a username that is available, it records the name as taken and emits a success message to an output stream. For every request for a username that is already taken, it emits a rejection message to an output stream. The client that requested the username watches the output stream and waits for a success or rejection message corresponding to its request. This algorithm is basically the same as in implementing linearizable storage using Total Order Broadcast on page 350. It scales easily to a large request throughput by increasing the number of partitions, as each partition can be processed independently. The approach works not only for uniqueness constraints, but also for many other kinds of constraints. Its fundamental principle is that any writes that may conflict are routed to the same partition and processed sequentially. As discussed in What is a Conflict? On page 174 and Write Skew and Phantoms on page 246, the definition of a conflict may depend on the application, but the stream processor can use arbitrary logic to validate a request. This idea is similar to the approach pioneered by Bayou in the 1990s. Ensuring that an operation is executed atomically while satisfying constraints becomes more interesting when several partitions are involved. In example 12-2, there are potentially three partitions: the one containing the request ID, the one containing the pay account, and the one containing the payer account. There is no reason why those three things should be in the same partition, since they are all independent from each other. In the traditional approach to databases, Executing this transaction would require an atomic commit across all three partitions, which essentially forces it into a total order with respect to all other transactions on any of those partitions. Since there is now cross-partition coordination, different partitions can no longer be processed independently, so throughput is likely to suffer. However, it turns out that equivalent correctness can be achieved with partitioned logs, and without an atomic commit. The request to transfer money from account A to account B is given a unique request ID by the client, and appended to a log partition based on the request ID. A stream processor reads the log of requests. For each request message, it emits two messages to output streams, a debit instruction to the payer account partitioned by A, and a credit instruction to the payee account B partitioned by B. The original request ID is included in those emitted messages. Further processors consume the streams of credit and debit instructions, deduplicate by request ID, and apply the changes to the account balances. Steps 1 and 2 are necessary, because if the client directly sent the credit and debit instructions, it would require an atomic commit across those two partitions to ensure that either both or neither happen. To avoid the need for a distributed transaction, we first durably log the request as a single message, and then derive the credit and debit instructions from that first message. Single object writes are atomic in almost all data systems. See single object writes on page 230, so the request either appears in the log or it doesn't, without any need for a multi-partition atomic commit. If the stream processor in step 2 crashes, it resumes processing from its last checkpoint. In doing so, it does not skip any request messages, but it may process requests multiple times and produce duplicate credit and debit instructions. However, since it is deterministic, it will just produce the same instructions again, and the processors in step 3 can easily deduplicate them using the end-to-end request ID. If you want to ensure that the payer account is not overdrawn by this transfer, you can additionally have a stream processor partitioned by payer account number that maintains account balances and validates transactions. Only valid transactions would then be placed in the request log in step 1. By breaking down the multi-partition transaction into two differently partitioned stages and using the end-to-end request ID, we have achieved the same correctness property. Every request is applied exactly once to both the payer and payee accounts, even in the presence of faults, and without using an atomic commit protocol. The idea of using multiple differently partitioned stages is similar to what we discussed in multi-partition data processing on page 514. See also concurrency control on page 462. Timeliness and integrity. A convenient property of transactions is that they are typically linearizable. See linearizability on page 324. That is, a writer waits until a transaction is committed, and thereafter its rights are immediately visible to all readers. This is not the case when unbundling an operation across multiple stages of stream processors. Consumers of a log are synchronous by design, so a sender does not wait until its message has been processed by consumers. However, it is possible for a client to wait for a message to appear on an output stream. This is what we did in uniqueness in log-based messaging on page 522 when checking whether a uniqueness constraint was satisfied. In this example, the correctness of the uniqueness check does not depend on whether the sender of the message waits for the outcome. The waiting only has the purpose of synchronously informing the sender whether or not the uniqueness check succeeded, but this notification can be decoupled from the effects of processing the message. More generally, I think the term consistency conflates two different requirements that are worth considering separately. Timeliness means ensuring that users observe the system in an up-to-date state. We saw previously that if a user reads from a stale copy of the data, they may observe it in an inconsistent state. See problems with replication lag on page 161. However, that inconsistency is temporary and will eventually be resolved simply by waiting and trying again. The CAP theorem, see the cost of linearizability on page 335, uses consistency in the sense of linearizability, which is a strong way of achieving timeliness. Weaker timeliness properties like read after write consistency, see reading your own rights on page 162, can also be useful. Integrity means absence of corruption, i.e. no data loss, and no contradictory or false data. In particular, if some derived dataset is maintained as a view onto some underlying data, see deriving current state from the event log on page 458, the derivation must be correct. For example, a database index must correctly reflect the contents of the database. An index in which some records are missing is not very useful. If integrity is violated, the inconsistency is permanent. Waiting and trying again is not going to fix database corruption in most cases. Instead, explicit checking and repair is needed. In the context of ACID transactions, see the meaning of ACID on page 223. Consistency is usually understood as some kind of application-specific notion of integrity. Atomicity and durability are important tools for preserving integrity. In slogan form, violations of timeliness are eventual consistency, whereas violations of integrity are perpetual inconsistency. I am going to assert that in most applications, integrity is much more important than timeliness. Violations of timeliness can be annoying and confusing, but violations of integrity can be catastrophic. For example, on your credit card statement, it is not surprising if a transaction that you made within the last 24 hours does not yet appear. It is normal that these systems have a certain lag. We know that banks reconcile and settle transactions asynchronously, and timeliness is not very important here. However, it would be very bad if the statement balance was not equal to the sum of the transactions plus the previous statement balance, an error in the sums, or if a transaction was charged to you but not paid to the merchant, disappearing money. Such problems would be violations of the integrity of the system. ACID transactions usually provide both timeliness, for example linearizability, and integrity, for example atomic commit guarantees. Thus, if you approach application correctness from the point of view of ACID transactions, the distinction between timeliness and integrity is fairly inconsequential. On the other hand, an interesting property of the event-based data flow systems that we have discussed in this chapter is that they decouple timeliness and integrity. When processing event streams asynchronously, there is no guarantee of timeliness, unless you explicitly build consumers that wait for a message to arrive before returning. But integrity is in fact central to streaming systems. Exactly once, or effectively once, semantic C fault tolerance on page 476 is a mechanism for preserving integrity. If an event is lost, or if an event takes effect twice, the integrity of a data system could be violated. Thus, fault-tolerant message delivery and duplicate suppression, for example idempotent operations, are important for maintaining the integrity of a data system in the face of faults. As we saw in the last section, reliable stream processing systems can preserve integrity without requiring distributed transactions and an atomic commit protocol, which means they can potentially achieve comparable correctness with much better performance and operational robustness. We achieve this integrity through a combination of mechanisms, representing the content of the right operation as a single message, which can easily be written atomically, an approach that fits very well with event sourcing. See event sourcing on page 457. Deriving all other state updates from that single message using deterministic derivation functions, similarly to stored procedures. See actual serial execution on page 252 and application co as a derivation function on page 505. Pass in a client-generated request ID through all these levels of processing, enabling end-to-end duplicate suppression and idempotence, making messages immutable and allowing derived data to be reprocessed from time to time, which makes it easier to recover from bugs. See advantages of immutable events on page 460. This combination of mechanisms seems to me a very promising direction for building fault-tolerant applications in the future. As discussed previously, enforcing a uniqueness constraint requires consensus, typically implemented by funneling all events in a particular partition through a single node. This limitation is unavoidable if we want the traditional form of uniqueness constraint, and stream processing cannot avoid it. However, another thing to realize is that many real applications can actually get away with much weaker notions of uniqueness. If two people concurrently register the same username or book the same seat, you can send one of them a message to apologize, and to ask them to choose a different one. This kind of change to correct a mistake is called a compensating transaction. If customers order more items than you have in your warehouse, you can order in more stock, apologize to customers for the delay, and offer them a discount. This is actually the same as what you'd have to do if, say, a forklift truck ran over some of the items in your warehouse, leaving you with fewer items in stock than you thought you had. Thus, the apology workflow already needs to be part of your business processes anyway, and so it might be unnecessary to require a linearizable constraint on the number of items in stock. Similarly, many airlines overbook airplanes in the expectation that some passengers will miss their flight, and many hotels overbook rooms, expecting that some guests will cancel. In these cases, the constraint of one person per seat is deliberately violated for business reasons, and compensation processes, refunds, upgrades, providing a complimentary room at a neighboring hotel are put in place to handle situations in which demand exceeds supply. Even if there was no overbooking, apology and compensation processes would be needed in order to deal with flights being cancelled due to bad weather or staff on strike. Recovering from such issues is just a normal part of business. If someone withdraws more money than they have in their account, the bank can charge them an overdraft fee and ask them to pay back what they owe. By limiting the total withdrawals per day, the risk to the bank is bounded. In many business contexts, it is actually acceptable to temporarily violate a constraint and fix it up later by apologizing. The cost of the apology in terms of money or reputation varies, but it is often quite low. You can't unsend an email, but you can send a follow-up email with a correction. If you accidentally charge a credit card twice, you can refund one of the charges, and the cost to you is just the processing fees and perhaps a customer complaint. Once money has been paid out of an ATM, you can't directly get it back, although in principle you can send debt collectors to recover the money if the account was overdrawn and the customer won't pay it back. Whether the cost of the apology is acceptable is a business decision. If it is acceptable, the traditional model of checking all constraints before even writing the data is unnecessarily restrictive, and a linearizable constraint is not needed. It may well be a reasonable choice to go ahead with a write optimistically and to check the constraint after the fact. You can still ensure that the validation occurs before doing things that would be expensive to recover from, but that doesn't imply you must do the validation before you even write the data. These applications do require integrity. You would not want to lose a reservation or have money disappear due to mismatched credits and debits, but they don't require timeliness on the enforcement of the constraint. If you have sold more items than you have in the warehouse, you can patch up the problem after the fact by apologizing. Doing so is similar to the conflict resolution approaches we discussed in handling right conflicts on page 171. We have now made two interesting observations. Data flow systems can maintain integrity guarantees on derived data without atomic commit, linearizability, or synchronous cross-partition coordination. Although strict uniqueness constraints require timeliness and coordination, many applications are actually fine with loose constraints that may be temporarily violated and fixed up later, as long as integrity is preserved throughout. Taken together, these observations mean that data flow systems can provide the data management services for many applications without requiring coordination, while still giving strong integrity guarantees. Such coordination-avoiding data systems have a lot of appeal. They can achieve better performance and fault tolerance than systems that need to perform synchronous coordination. For example, such a system could operate distributed across multiple data centers in a multi-leader configuration, asynchronously replicating between regions. Any one data center can continue operating independently from the others because no synchronous cross-region coordination is required. Such a system would have weak timeliness guarantees. It could not be linearizable without introducing coordination, but it can still have strong integrity guarantees. In this context, serializable transactions are still useful as part of maintaining derived state, but they can be run at a small scope, where they work well. Heterogeneous distributed transactions such as XA transactions, see distributed transactions in practice on page 360, are not required. Synchronous coordination can still be introduced in places where it is needed, for example, to enforce strict constraints before an operation from which recovery is not possible, but there is no need for everything to pay the cost of coordination if only a small part of an application needs it. Another way of looking at coordination and constraints: they reduce the number of apologies you have to make due to inconsistencies, but potentially also reduce the performance and availability of your system, and thus potentially increase the number of apologies you have to make due to outages. You cannot reduce the number of apologies to zero, but you can aim to find the best trade-off for your needs, the sweet spot, where there are neither too many inconsistencies nor too many availability problems.